Topic 4 is all about oscillations and waves. And I'm going to start off with the first subtopic within that, which is simple harmonic motion. A lot of times we call that SHM for short. That's just simple harmonic motion. Now, what actually is an example of simple harmonic motion? That could be something like a pendulum. So for example, if I use my arm right here and I just let it sort of hang and then just oscillate back and forth, that could be something in simple harmonic motion. So can a spring. Okay, so those are two examples. Is a spring or a pendulum. Now I'd like to think about, I'm going to use a spring as an example a few times. So what I'm going to do is just draw you roughly what I mean here. Let's say I have a spring here and I have some sort of mass attached to it. Then I have other springs over here, and then I have some sort of wall and a wall. This is the ground here like this. So what could happen then is this mass, if I give it a little push, this mass will sit there and oscillate back and forth. Now what makes it simple harmonic motion is that, well, first of all, every time you push it one way, it's going to feel a force in the opposite way. That's the key, that's one of the key things at least. And so let's take a look at this. Also, by the way, the acceleration of it's going to be proportional to how far it is. So I'll show you that in a second. So let's look at what it actually means. So we have simple harmonic motion if. Now I'm going to write down a few things here. We're going to hopefully see what this means. So this example, or this equation here is not in your data booklet, but I would strongly recommend memorizing this one. This is probably the most important one here to memorize in this topic. This is A equals minus omega squared x. Now I'm going to define what each of these means. That might help. So A is the acceleration. So that one we're used to. Has regular units, which is meters per second squared. Now we have x, which is the displacement from the equilibrium position. That's the key thing here, okay? Displacement from, and I'm just going to say equal position. That's short for equilibrium position. That's going to be measured in meters. What I mean by that is that right here, if I left this mass on a spring, long enough, it's going to sit right there in the middle. And if I displace it, so let's say I moved it over, over to here. Let's say it was sitting over here, then that distance right there, that would be x. Okay, that would be my distance or my displacement from equilibrium. In other words, how far I've moved it from where it wants to sit. Same thing with the pendulum. If it goes back and forth, if you let it long enough, guess what? It's going to just be straight down. Or my example earlier with if I had a bunch of cats, for example, and I used them as a pendulum, and I was doing something with different lengths of cats and seeing how their period of oscillation changed. Well, these cats would actually be in simple harmonic motion because, well, first of all, they have an equilibrium position. In other words, if I let it long enough, it's going to stay still. So that's one of the things here. And this displacement from equilibrium position, that's x. Now omega is something new. Okay, a lot of people haven't seen this before. This is an angular frequency. Now that's measured in radians per second. Now, if you haven't heard of a radian before, this is a thing that we do in math, especially in math SL and math HL. So if you look at that, a radian is basically if you go all the way around a circle, then you've actually gone what we call 2 pi radians. So it's basically, it's a neat way of actually looking at angles. So instead of doing things in degrees, we actually do them in radians. Not to worry too much, it's just got a weird unit. Now, we've actually got an equation here for it, which is omega equals 2 pi over t, where t is the period. And it's also equal to 2 pi f, if you prefer. Now, this right here is on your data booklet, 2 pi over t, where t is the period of oscillation. That's how long it takes for it to go one full oscillation. So if it's a pendulum, it's how long it takes to go, let's say, from here over to the end and then back again. Or if it's this spring situation, it's how long it takes for it to go, I don't know, maybe from the end here, back, and then back to the end. That's the period. Whereas F here, that's the frequency. That's also something very important. And that's actually measured in what we call hertz. We're going to be talking more about frequency a little bit later. But for right now, I just wanted to show you a little bit about what each of these actually is. Now, when I said we have simple harmonic motion, I haven't really explained exactly what I mean. But it turns out this equation...
Insvept i guld. Den nya espressokapseln från Laura. Den första aluminiumkapseln som du kan köpa i mataffären. Designad för att passa din espressomaskin. Låt dig förföras av en espresso med guldstandard. Laura. Why pursue anything less than gold?
A versus X. So the acceleration in meters per second squared as a function of X, which is the displacement from equilibrium in meters. And the graph is going to do something actually quite special. Now think about it carefully here. I want to linearize this, which means I'm going to put this as the y value. I'm going to make x the x value. And that means that this omega squared, that's going to be the slope or gradient. And I expect it to have no y-intercept. Well, not that it has none. It's just that the y-intercept is 0, because I don't have a plus something term. So because of that, I expect it to pass right through the origin, because there's no plus something. Right? If it was like plus 2, then it would cross through y equals 2, or a equals 2 in this case. But because it has nothing there, so then it passes through the origin. The negative means it's going to be a slope that doesn't go like this, but instead it's going to be a straight line that goes like this. So that's all the negative does. So once you've factored that in, it doesn't really matter. And I could say then that the graph goes something like, well, I just need to make a straight line here. Say a straight line like this. This is a graph of a equals minus omega squared x. So that means that the slope, or the gradient, is just equal to omega. There are two key points to simple harmonic motion. Okay, the very first one is that the acceleration is proportional to x. In other words, look at this. So the more x I have, in other words, the more displacement from equilibrium I have, the more acceleration I have. And so the less displacement I have, the less acceleration. That's what this means here to be linear. So this is the key, sort of first key thing here to know if you have simple harmonic motion, is that the acceleration is proportional to the displacement. And the second one, okay, this is actually really important here, is that the acceleration is opposite, let's say, in direction to the displacement. So those are the two key points here, I think, that are the important things here that come about. That actually comes from this equation right here. So if I were you, what I would do is actually try to remember this equation here, a equals minus omega squared x. From there, if you know how to linearize, you can then draw this graph. And this graph actually tells you everything you need to know. See, what's key about it, what's really cool is that, well, the first step that comes from this, it just says basically this is linear. That's what I mean by proportional. Okay? In fact, in this case, it's directly proportional, which means it goes past through the origin. That means the bigger x value, the bigger a value. Right? The letter less x, less a. If you have negative x, then you have a. But notice how if you go large x, you have negative a. That's this second one here, that the acceleration is opposite in direction to the displacement. So that means if you go out in positive x values, you have negative acceleration. And if you have negative x direction, you have positive acceleration. And what this means in real life here is, take a look here. If I displace this, let's assume that this is 0, so anything to the right is positive. What this tells you is that as I displace this thing to the right, which means a positive displacement, my acceleration is going to be opposite in direction. In other words, if it's displaced this way, the acceleration is the opposite, which is this way. So what that tells you is, as you pull it one way, it wants to be pulled the other way, because acceleration, you can use F equals ma, for example, Newton's second law, and say that an acceleration implies a force. So what this tells you then is, as you pull it one way, it's going to feel force the opposite way. And then as you pull it this way over here, it's going to feel force that way. See, that's what the second one says. It's basically no matter how you pull it, the force is going to be opposite to what you've done. It's almost as if it can't decide what it wants, right? You pull it one way, it says, wait, come back. Right, then you go over here, it says, go away. So it's like something that just keeps switching in direction. Same thing with the pendulum, right? If it's over here, what happens? I've displaced it over to the right, which is maximum displacement over here. What happens then is the force goes that way, right? It goes sort of back down that way. And as my hand is over here, what happens? Well, then the force goes that way. So the force is always opposite in direction to the displacement. So that's why this, I think, is the key thing here. Knowing how to linearize gets you this graph. And this has come up many, many times on exam questions. This is a very common exam question. This is asked very often. So this is really important to know how to use. And I think it's actually not nearly so hard as it seems once you know how to linearize and you remember that equation.
Yeah, sure. Does it? Ventrum.
I thought it would be useful to show you an example of something with simple harmonic motion and go into a little bit more detail, especially looking at the energies involved. So let's say we have an example here, and we have let's say you have a spring moving back and forth. Actually, you have a mass on a spring, and we're going to assume that it's frictionless and all that good stuff. So let's just take a look here at this object here. So this is my little mass, and it's connected by a spring on one side and a spring on the other side. Maybe those are connected to walls. This is the ground here. So what I do, of course, is I let it be right here. If I just let it sit there, this right here is x equals 0. This is the equilibrium position.
Oh, nice try.
Nice try, dude.
Equilibrium position. So what happens then is that, let's say it
like
can
a
move
guy's
all
based
the way
off
to the right. Maybe it moves all the way over here.
Cisco.
Maybe it can move all the way to the left, over to here. In other words, it can go kind of back and forth and back and forth, back and forth. Well, the key thing then is to take a look at these different situations and see what the energies are
Why
doing.
about again, bro?
So remember that the kinetic energy
both.
is all about the
Nice.
motion and all about the
It doesn't
speed.
have,
So the kinetic energy is half
Does he even
mv
hear us?
squared. Remember that, EK is half mv squared.
I believe so.
Oops. So that means
No HP.
that if it's got no speed, then it's got no kinetic energy. And that happens over here and over here. So let's maybe write over at the end here. You know when it's going back and forth? The way I remember how to work with simple harmonic motion and these graphs, I just think of this thing, that's all I start with, and I work out the rest. So I'll show you what I do.
Look, it's
At the
OG.
very end right here, okay, it's actually going to stop for an instant. So because of that, V equals 0. And over here at the other end, also V equals 0. This is actually symmetric. So anything on the right side is the same as the left side. So over here then, what happens then? Well, that means that
mouse is banked
EK equals 0. And over here, EK equals 0. But over here then, we also have potential energy. We have stored energy. Now in a spring, you have stored energy as well. Right? The more you squish a spring, the more it sort of wants to push back. So that's potential energy as well. A lot of people are used to only thinking of potential energy as gravitational potential, by going up in height. But springs have potential energy as well. And the key is just imagine the more squished a spring is, the more potential energy it has. So that means we're going to say that EP, the potential energy, is at a maximum. I don't know what value it is. I'd have to know about the spring constant and other things. But the key
My
thing here is that the
ace!
potential energy is at a maximum here. Over here, same thing. EP equals max. Now what happens here at displacement 0 though? At that point, we actually have that the speed is at a maximum. And that's because as it's flying by, you know, over here it's going its fastest point right here, and then it slows down and stops, and it goes fastest right here, and then it slows down again, and then back and forth, back and forth. So because V is at a maximum, that means EK is at a maximum.
Evan?
And remember I talked about how much a spring is squished? That tells you about its potential energy. So that means if it's in the middle, neither of the springs is squished. You know, that's at its equilibrium position. So that means that the potential energy is 0. So that means then that we could do a graph of, let's say here, we could actually graph if we wanted, I could graph the displacement in meters, and I could graph that against the energy in joules, let's say. Now what I could do then is take a look, okay, at 0 displacement, because remember this thing can go negative and positive, right? Because this is my displacement from here, so this is a positive displacement and negative. So I'm going to have to draw it in the positives and negatives. Well, at 0 displacement, what is its kinetic energy? Maximum. So it's some value up here. That's maximum kinetic energy. Then at the maximum displacement, you know, way over here at the end, its kinetic energy is 0. So what I'm going to do right now is graph kinetic energy. So it turns out kinetic energy is going to do something like this and then something like this, assuming that this right here is as far as it can go. So basically, as you stretch it all the way over here, there's no kinetic energy. This is going to be a graph, by the way, of EK, kinetic energy. So at this end over here, at that maximum displacement, that's where you have no kinetic energy, right, because it's stopped. As it has 0 displacement, it's at maximum kinetic energy. That's because it's moving as fast as it can. And the same thing over here, it's symmetric, so that means as negative maximum displacement, you still have 0 kinetic energy.
What the fuck?
Well, the potential energy does the opposite, right? At this point right here, there was no potential energy, so maybe I'll draw this in green here.
What?
And over
That's a
here we
fuck.
have maximum potential energy.
That's flick, man.
And over here we have a maximum. So it does,
Then
the
80
graph,
flick.
it does like this. This is EP. So graphing energy versus
by the way. Check his
displacement,
profile.
then we have the kinetic and the potential
Moving.
doing this.
Täta player. It's a bulk account.
But we could also graph something else.
Oh yeah,
What if
right.
we look at the total
Okay.
energy? E total.
500,
That's going to be
of
just
course.
the kinetic
That is
plus
obviously
the
fake.
potential energies. So maybe we'll want to graph, in this case right here, a different type of graph here. But same sort of situation, except now, let's say instead of graphing displacement
can
on
buy
the
that.
x-axis, I'm going to put
I
time.
want 50.
That's going to be in a second. So the key difference between this graph and this graph is that I've got
Flash.
time on the x-axis. So if I do that, and I still graph energy in joules over here,
Backs down.
well, it all depends on when I start my timer, so to speak. So let's just say I started my timer, you know, I mean, it's moving back and forth, but let's just say I start my timer right here when it's at
Indicator HP.
displacement equals 0. Well, that means then that my kinetic
2
energy
HP and we
will be at a
gain
maximum
Nade.
at time t equals 0.
Well,
And
that's
that kinetic
minus.
energy will actually go sort of down and then maybe back up. This is
Nice.
going to be sinusoidal. In other words, it's going to keep going. Right, so this could be my
Far behind. What the fuck?
EK. That's my kinetic energy. That's because let's just assume that I started timing right when it was passing by that 0 displacement. If that's the case, then it would look like this. If I started timing at a different time, it's okay. This whole thing would just be shifted, but who cares? It still has the same shape. It would just go up and down and up and down. Now remember, that's different from this one because this is displacement. This doesn't just go like this because it only has a maximum displacement and a minimum displacement. As it
Can I
goes
get an
back
indicator?
and forth,
Okay.
its value is basically going to go like this of kinetic energy as it goes back and forth. The potential will go back and forth, sort of opposite, right? So that's why they go like this and like this and like this. However, here, if I went over time, this is something that would just go on forever. So this is a different scale altogether, or a different graph altogether. Now the potential will do the opposite, right? So over here it's going to be 0. Over here then it's going to go to a maximum and then back down to a minimum. So that right there would be EP. Just make sure I
Checkers.
make that as clear as I can.
Yeah.
So that's the potential energy would be in green here. But the cool thing is what if I looked at the total energy, which means in this case I add up the kinetic plus the potential at every point. That means over here I add up whatever value this is plus 0. Over here I add up this plus this. Over here I add up this plus this. If I did that, I would have a straight line going across, and that right there would be the total energy. In other words, remember we talked before about how energy can change form, but the total energy remains the same. Well, in this case, that's precisely what's happening here. That if I have this situation here where it's a perfect situation, there's no resistive forces, there's no friction, there's no air resistance, nothing like that. These graphs right here would keep going like this forever. They go the same height. Now what happens in real life? Well, we have friction on the ground. You know, in other words, this thing is going to drag against stuff, so that's going to be a problem. There's going to be air resistance, there's going to be noise, there's going to be all sorts of things. So as a result, real life situations don't go on like this forever.
Nice.
They do what we call damping. In other words, these right here are going to get smaller and smaller and smaller. And that's actually because, you know, the oscillation. I mean, just imagine a real pendulum. Remember I had my cat's example. So I hang my cats happily, of course. Let's say we just hold the cat by its sort of head and its arms. I guess they're called front paws. I think. I'm not a cat expert, so maybe you are. But if I just sort of, you know, move the cat around, you know, its legs and sort of bottom part of its body is just going to go back and forth. If I left it, you know, if I just sort of gave it a little shake and then let it go, the cat, of course, would end up going back and forth, but less and less and less and less until it eventually stops. That's the case with any pendulum. And that's because in real life, there's what's called damping. Because the forces, so frictional forces and gravitational forces, all sorts of things are going to act, not gravitational exactly, but frictional forces, air resistance, those are going to slow things down and cause for energy loss. Some of the energy will go towards other things. Right? If it's friction like this, if you move this back and forth, friction is going to end up meaning that the surface is going to get hot. Right? I mean, if I take my hands and go like this, I don't know, you can't really feel it, but it actually gets hot. That means some energy went to heating. Right? That's thermal energy. So I think simple harmonic motion, this is a nice way to think about it, is just think of an example, maybe like a spring here oscillating back and forth. Then you can sort of figure out what the graphs of energy, kinetic, and potential would look like versus displacement, as well as looking at it as a function of time and see how it relates to the total energy. Looking at simple harmonic motion, sometimes the equations are what really gets students a little bit nervous, especially when you look at the equations for SHM. Okay, so for simple harmonic motion, equations look a little bit wacky. So I'm going to show you them and hopefully show you how easy they are actually to work with. So the very first equation that, well, there's a whole bunch of them. I'm not going to show you all of them, but I will show you a few. So one of the main ones to show you then is this one. It goes x equals x0. And then what we do is we multiply that value by sine omega t. So it's going to help maybe to define what these are. And before I do that, maybe it helps to remind you again what we're looking at for simple harmonic motion. Let's say I've got my really boring example of some object that's sitting on the ground here, assuming it's frictionless, and it's got a spring at one end, and it's got a spring at another end. So it's oscillating back and forth. And this is a value x equals 0. Now it might go to a maximum value here, and it might go to a minimum value here. So maybe it sort of oscillates between these points. Okay, back and forth, back and forth. Well, then it might also be interesting to look at the energy of this, just to remind you about how that graph looked. So also, if I wanted to try to look at the energy, what I could do then is actually graph, well, if this is the position, this is the position where I am. So if I've got x here, and this could be the energy, which is in joules, well then, whoops, I should probably put my axis somewhere right in the middle, let's say. So this is the energy as you go up and down here. Well, what will happen is the kinetic energy
One
will do
close, man.
something like this.
Watch out.
We'll do something like that. Okay, so that will be EK. So what that means then is that at x equals 0, there's a maximum kinetic energy. That should make sense from what we looked at before, because at
got
x equals 0,
27
that's when
into
it's right here.
Wednesday.
That's when it's going to be moving the fastest. Remember, over here it's stopped. Then it turns around and goes, and it's traveling as fast as it can right here. Then it goes, slows down again, and stops here. Goes back again, fastest here.
Dude, why are you
So the
flashing me?
maximum
Nice, bro.
kinetic energy, the EK highest value it
What the
reaches,
fuck?
is at x equals 0. So right here at x equals 0.
Hey.
Now
Why
we also have
didn't
the
you say
potential
that?
energy, and it actually
We
works in the
said that.
opposite way. So potential energy will be something like this. So
Physics.
this will be EP.
Yeah.
You're listening
That means
to
then at
NASA.
x equals 0, it has no potential energy. That's because the springs aren't really pulling on it much. Whereas when it's over here at its maximum displacement, that's when it has a maximum potential energy. And that's because it's got all the stored up energy because it's just stopped and it wants to really go flying that way.
Nice.
Or opposite, like this.
Nice.
So looking at this, how can we relate all this stuff to these things? Well, this is the first equation here. And maybe we should define some things. So the very first one is x. X is your displacement. That's your, maybe I'll say actual displacement. Maybe that's better. Actual,
My friend, NASA is more
Displacement.
important than info.
that'll be measured in meters.
Yes.
Well, x0 is going to be your maximum displacement. Also measured in meters.
Can you stop?
So x is your actual position. You're sitting here, you're at x equals 0. Over here, you're at x equals whatever. Over here, you're at maximum displacement. So that's when you're at
What the
x0.
fuck? Lol.
Now, we have t, which is the time. That's in seconds. And we have omega, which is the angular frequency,
What's the...
which is actually measured in radians per second. Some people like to measure it in hertz. But this is the angular frequency.
Yeah, absolutely must.
So what this means then is that you can figure out what your actual displacement is depending on what time you're looking at, so to speak. Right? So this right here will basically tell you how many radians you've gone around if you think carefully about the units. Because you've got omega, which is in radians per second. If you multiply that by time, which is in seconds, the seconds cancel out on the top and the bottom. So you just have a sine of some angle in radians. And that's going to be just multiplied by your maximum displacement. You're rarely asked to actually calculate this, but it's still a good idea to know how these work. Now we have another equation as well. So this right here, this is one for the kinetic energy at any point. And it's going to be 1/2 m omega.
Beside.
Now this one here,
These
the
are
omega is going to be squared here. And we're going to multiply that by x0 squared minus x squared. So that's what we're going to be doing here. So this equation right here, this tells me about the kinetic energy of this thing going in simple harmonic
Got
motion.
someone drop.
This is its kinetic energy at any
Oh, I
position.
don't have money.
Remember, again, this m is just your mass. That's your mass in kilograms. And EK is your energy in joules. So what's happening here is we have a difference of squares of your maximum displacement compared to your actual displacement. Then we have an equation here for EK max. This tells you the maximum kinetic energy. And I want to show you how we can figure out what happens here. So this one right here, the equation goes like this. 1/2 m omega squared times x0 squared. And that's it. Now why would that be? Look at this. This EK max looks just like the EK one, except there's no minus x squared. So let's think about what happens here. We want to know the maximum kinetic energy. Now think about it over here, though. Over here, this little white curve here, that's the kinetic energy, depending on your position.
And I'm friendly.
So over here, at maximum displacement, we have 0 kinetic energy. Whereas at 0 actual displacement, we have a maximum kinetic energy. So at
why are we
maximum
learning
kinetic
some
energy, we
nice
have x
technology?
equals 0. So at max kinetic energy, x equals 0.
2 mid, 1 pushing, 1 close.
That should make sense. Right? If you look at this graph here, the kinetic energy curve is the highest when x is 0. So all you have to do then is set x here equal to 0. Well, setting that equal to 0 means that disappears. That should explain why EK max is just this, half m omega squared x0 squared. That's it. Now the last and final equation tells you about the total energy. So the total energy, they tell you it's just this, 1/2 m omega squared x0 squared. You might think, is the total energy really equal to
I'm
the
gonna flash from
maximum
above.
kinetic energy? Because these are the
It's
same.
left side mid.
Let's see if that makes
Okay,
any
okay.
sense. Now the total energy,
You had reload.
total
It
energy,
was
ET,
close mid to
is
main.
just equal to the potential plus the kinetic.
Good job.
Okay, so that we've learned before. The total energy is the kinetic plus the potential. So that means if we look at this graph over here, that means the total energy at any given x point is just add up the potential plus the kinetic energy. So if I did it, let's say right over here at this x value right here, well, I would add it, or maybe this value right here, let's say.
Purple.
If I did it right here. If I'm looking at that x value right there,
What?
what's the total energy? Well, it would be
Why
whatever
are
that
you
potential
learning some
energy is,
nice
whatever that
technology?
value is, plus
Because I have
whatever this
my
value is, because that's the
test coming
kinetic.
up.
So it'd be that potential plus that kinetic.
Oh.
Okay, so we can do that for any point. But why not make our
do have
lives
nothing.
easier? Again, look at maximum kinetic energy. Look at when
My
we
aim is
choose
shit.
x equals 0 here. What happens then?
Fucking
then-
garbage.
The potential energy is 0. So I'm going to say, but at x equals 0,
1 CT.
EP, whoops, the potential energy equals
Nice.
0, and the kinetic energy is EK max.
Nice try, bruh.
So hopefully that makes sense. If we just arbitrarily pick x equals 0 here, if we make x 0, well, the potential energy is 0 at that point, only there, and the kinetic energy is at its maximum, so that's EK max. So because of that, then, I end up with ET, which is supposed to be EP plus EK, but the EP cancels out. So I have ET equals EK, and at that point it was max. So that's hopefully explaining why the total energy is actually the same as the maximum
my
kinetic
fucking
energy. Only because we happen to choose that x equals 0 there. We could actually find the
I
total
aim at
energy
his head, I don't get
anywhere
headshot.
else
What
if we
the
wanted.
fuck?
And there we just have to add up the kinetic plus the potential energy. You could be asked then at a certain point, maybe they give you an equation. Maybe they say the total energy equals this crazy equation. And they say, and the kinetic energy is this. What's the potential? You can easily figure that out. Because all you have to do is just look at, well, the potential is going to be the total minus the
My
kinetic.
fucking god.
So it all depends on where you picked. So you can't
Nice
just
try,
say the
boys.
total energy,
Nice
oh,
try.
potential energy is always 0. No. This was a special case. So this always works here, that the total is potential plus kinetic. But at this specific
hate my
point,
life.
if we
I aimed
choose
right
x
in the-
equals
of
0,
his head.
then the potential is
get the
0
headshot.
and the kinetic energy is EK max. Therefore, we
aimed
can
in the
say
middle
that
of
at
his
that
eyeball.
point, E total is EK max. Now, of course, this works for any situation, any x value that the ET is equal
That's
to
a technology
EK max.
doesn't work here.
But what if we're not given the maximum kinetic energy? What if we're just given the kinetic energy at some general point? Maybe we're given the kinetic energy here at this x value. Well, then if you notice, then you have to be more careful
All
and
in one
consider
minute.
the potential energy and the
AVP.
kinetic energy.
There's the AK.
So this is how it works. And hopefully you'll see that these equations, there's no reason to sort of freak out when you see them. They may look awkward, but it's just a matter of decoding what everything means. The
Open
key thing to remember is that
squeaky
x
door
is your
and
actual
stand behind it.
displacement and x0 is your
Hello?
maximum displacement.
That's the thing soldiers say. Aim at
The
someone.
second thing I'd like to talk to you
Let's
about
headshot.
under waves is just general properties
working.
of
Yeah,
waves.
well, not in this
I
game.
think the most important equation, for example, is this
Can
one
I
right
get a
here.
name for
V
Kalinka?
equals F lambda. It's in your data booklet, so it's extremely important. Some people call this the wave equation. So this one right here, V, is the speed of the wave, which is in meters per second. We have F, which is the frequency, and that has units of hertz, or you could say it's seconds to the -1. That's the same thing. Okay, basically, how many
Taking a
times
break,
per
mate?
second
That's
does something happen? If you think about frequency, one common
Hello.
use of that is in a
Recommend.
computer. If you think about how fast your computer is, you know, it might be 3 gigahertz. So that tells you it's 3 billion operations per second it does. That's what 3
Why is he
gigahertz
looking
would
at?
be. So
Okay, yeah.
we also have lambda, which is this little Greek symbol right here. And that is actually the wavelength. And that's measured in meters. So this basically tells you how to get, if you get frequency, then you can convert
It's
that
gonna
to
be-
wavelength if you know the speed. This works for water waves, this works for
Got
light
the C4.
waves,
Everyone
this
rotate
works
to
for any
four
kind of
orange.
wave. That reminds me of a really lame joke, maybe you'll like it. It's really short. If you saw a light wave, would you wave back? Oh, it's actually bad, sorry. But here, if we look at this wave equation, this tells us a lot. In fact, if we're
64
looking at
hours
light,
and can do that
so
without
if this
noise.
speed of light in that case then becomes c,
Ball bang
at least if we're in a vacuum, so we could make that value, you know, c, which is 3 times 10 to the 8 meters per second. And if we do that, then we can see that the frequency tells you the wavelength and vice versa. And in fact,
No,
what I
that the
like about
frequency
light is
can
that
tell you the wavelength.
the color tells you the wavelength.
No.
In other words, if
Oh, you
something
do.
looks red, then I know at least that red-ish things, at least to our own eyes, those are around 600-ish nanometers. In other words, 600 times 10 to the minus 9 meters.
No, that
Whereas
red
blue
color
will
is
be maybe
600 nanometer.
488 nanometers.
No.
I think it's amazing that your
Oh,
eye
you do.
can actually tell the difference between just a few hundred nanometers will look totally blue versus totally red. And so there's lots of different
minus
colors
70.
out there and lots of colors that we can't see. Part of the curriculum actually asks you to sort of have an idea about the whole light spectrum.
Free fire, man.
But basically the key thing there is that color tells you the
Nice.
wavelength. Right? Because color and wavelength are in a sense, they're the same thing. Right?
Maybe
so
you
if something
can do
has
it. One is minus
a
70.
wavelength that's way past red that we can't see, that's what we call that infrared. And if something is way bluer than blue, in other words,
Maybe you can.
smaller wavelength than what we can see,
Yeah, we need
well, if
more.
it's bluer than
more
blue, we
be-
call that ultraviolet. And of course, we have all the
could be
different
now.
things way at the extremes. We have, you know,
Don't worry, I got
X-rays,
B now.
we have microwaves, we have radio waves. All those
Okay.
things are just a different color of light. The
They're-
colors of
they're
light we can't
shiny.
actually see.
Gonna fuck
And
their
we can only
aim
see
as long as
between
they
about
don't require my
400-ish
help.
and 600-ish nanometers. Well, 700. It all depends. But if we look at this, then that's the first
Uh-huh.
wave equation.
I
Now we
wanna
can
fuck
actually
them.
have some properties of any wave. So if we take any old wave and we graph its,
Oh my-
let's
okay, it's
say,
fucking hacking, I say.
position.
Yeah, bro, you
So
saw
this
that
will be some sort of
thing it did without
value
please me.
here
I'm coming.
in meters
Yeah, well, they're
versus
pushing
a
me now, I don't know.
displacement.
Maybe highway.
They broke the
So here I'm looking like an actual wave, okay? So something that actually goes up and down. I've got two things, right? I can measure its displacement, in other words, its height, but I can also measure the position. So in that sense, if I'm graphing position versus height, and I have any old wave, it can do whatever shape it wants. Let's just say it does something like this,
Mid.
and it can actually go back. I mean, this thing could go forever. If I graph that then, this height right here,
Fence,
so
fence.
from the middle point to the maximum height,
Speed.
we actually call that the
Fence.
amplitude of
Nice,
that
man.
wave.
Last was mid. Last was
That's
mid.
the sort of from the middle to the top. Because it goes up above that value, it also goes
Left,
below
left,
by
close.
that value.
Pistol,
That's the
pistol
amplitude.
green.
And if we could measure the distance from here to here, right, from one peak to a peak, or it could be
Nice.
from a start point to a start point, in other words, from where it crosses the x-axis, going upwards, you know, and then upwards again. So that distance here is actually the
Can I
same
get the
here.
drop?
It's also the same as,
Thank
let's say,
you.
from a minimum to a minimum. All this distance right here is actually
got an
going to be the
M4,
same.
blue?
That's actually what we call the in this case, the wavelength.
Why does he
So
get
that's
that
the
skin?
wavelength measured in
can
go
meters.
then.
By the way, the amplitude is also measured in meters. So if we could measure that distance from this peak to peak, or a trough to a trough, or wherever, that's the wavelength. So with the wave, we can also
They're
draw,
shooting
this is
behind
sort
that
of
fucking
position.
smoke.
We can also draw a wave based on time. So if we put time in seconds,
Your friend
and this time we still graph the displacement. Because a wave can actually go, I mean, a wave might actually be traveling, maybe it's like, whoa, when it's moving. And if we know at least something about that wave, let's say it's
Beside
drawn
nest.
a similar looking wave like this,
Oh, you're on your own.
then this distance from here to here now, it's no longer the wavelength. See over here, we were measuring a position difference, from somewhere to somewhere. That was position. If we graphed time, however, then we could say that this right here is some sort of temporal measurement. In other words, some measurement
Can
of time.
someone push with me
In
mid?
this case, we would actually call that the period. We often
Can
write that
someone
with
push with
capital
me
T,
mid?
and that's measured in seconds.
It's
So that's actually, whoops, I should have probably written that in green. So we have the period. I probably just made that look a lot uglier now. Basically, we have the period T in seconds. That's going to be this distance
Maybe not
on
flashing
a
me.
time
Sorry.
graph. That's all the different things
We
that
got
we
the
might
C4.
want to know about, I think, with these. One other relation, though, is to see how frequency is related.
watch B.
And
Watch
frequency
B.
is 1 over the period. That's another equation right there. Okay, so F is the frequency in hertz,
On sandroom.
and you can
what?
see the
Sorry,
units now, because
one
if you take the
already
period,
NBK, what
which
the
is
fuck?
measured in seconds, do
2
1
and A.
over seconds,
Oh, we got
clearly
the
the
C4.
units are 1 over seconds. And that's actually called hertz. No, not that it hurts to do it. We mean H-E-R-T-Z. Or Z if you're American.
Yeah, nice.
So in this case right here, that's what we need to know about generic things about waves. Now we've actually got two types of waves. We've got transverse waves. And a transverse wave is a wave where the direction of oscillation is perpendicular, and I'm going to use this little symbol. A lot of times in
Well,
math,
that's
we
nice.
actually use this.
Fucking
This means
potato reaction.
perpendicular because it's either 90 degrees.
But you killed
It's
3
perpendicular
people, so
to
yeah.
the direction, whoops, of travel. So what I mean by
I have
that,
the
I'm going to give you an
reaction of a
example here.
potato.
So it could be light. So what we mean here is that the direction of the oscillation, because a wave will be something oscillating up and down or back and forth, but the thing is, if it's a transverse
again.
wave, it means that the direction that it oscillates is 90 degrees to the direction that it travels. So in this case right here, if it's light and it oscillates back and forth like this, okay, so if light oscillates back and forth, in this case if it's light, it'll actually be an electric and magnetic field. Turns out electric
One
field might be
speaking.
this, magnetic field might actually be
Low
back and
HP
forth,
speaking.
but the direction of travel will be this.
Yes.
So that could be light. See, light travels this way, and yet the
I'm gonna
oscillation
John
is up
Wick
and
this
down.
shit.
Another example could
My name is
be
John.
a water wave.
John Wick.
Same thing.
Watch.
One mid, one.
So if you imagine a wave of water coming
But I
by,
can't shoot.
you can imagine yourself sitting in the water, and then what happens is as a big wave comes up, the wave goes, up, whoa, and then you go down as the wave travels. What happened then is the oscillation went up and down, and yet the wave traveled 90 degrees to it, or perpendicular to it. Now we have another type of wave, which is longitudinal. And that is when the direction of travel is parallel. Direction of oscillation. That's what I meant to say. Direction of oscillation is, and we use this symbol here for parallel
Boost.
to direction of travel.
One at B, two
So in
at
this
B,
case,
one
I
at
could be
57.
talking about, for example, sound. So sound waves are actually like this. If I've got little molecules of air, and I've got other molecules here, I'm actually going to oscillate them back and forth and yet the way that it travels also travels that way. So in that sense,
Bro, I have freaking echoed
like this right here. So that's an example of a longitudinal wave. So sound, for example, which is what I'm doing right now as I speak, I'm actually creating these areas where there's compression of molecules and also areas where there's not so much. So that's actually called a rarefaction. So I've got places where there's more molecules together and then there's less molecules. What's happening is, as I'm speaking, I'm actually causing them to vibrate back and forth, and that travels in that same direction, or at least parallel. So that's the difference between longitudinal and transverse. So by looking at different properties of waves, we can understand and solve all sorts of types of questions. Just remember, though, that there is a difference between transverse and longitudinal. Those are very common exam questions, as well as asking you to draw or graph, or they give you a graph and ask you to know things about either the frequency or period, or wavelength, or amplitude. And I think the key equation here is this V equals F lambda. That's a way to convert from frequency to wavelength, or find the speed, right? And basically you're normally given two of these variables and you have to find the third. So I think those are the key sort of basic definitions and basic properties of waves. Another topic under waves is reflection and refraction. These two are what some people call basic things. In other words, if you've taken a physics class before this diploma, then maybe you've already learned about these. I'm going to do a very quick reminder. So what is reflection? Well, reflection is where, so let's just assume we have a wave coming in and then bouncing off something. So in that case, it could be anything. This could be light, it could be a water wave. If this is the surface that it's reflecting off of, so in this case, maybe it's a mirror. So this could be just like a solid surface here. And what we have to do is draw what we call a normal. In other words, we draw a line that's perpendicular to this surface. We normally draw it as a dotted line. What we'll do then is take a look at the incoming angle. In other words, something that's incoming. Closer. This could be a ball bouncing off a wall. It could be the direction of travel of a light wave. It could be a water wave that's coming in like this right here. Keeping in mind, though, the water wave will actually be little, pieces like this. The waves will actually be this
Take your
way,
pistol, push him from above the
travel
stuff.
will be given by that arrow. And we define the angle of incidence. We can call it theta 1, let's say.
In the smoke, maybe.
And that angle is always defined from
green.
the normal.
Why would
So
he
once
go
in a while,
this?
they're going to try to ask you a trick question on an exam where they actually give the angle from the surface. So don't get tripped up by that. The angles for reflection and refraction are always defined by how they are from the normal. And in this case, we're here.
Bros never fake, man.
And we're going to have that.
No time.
Theta 1 equals theta 2. In other words, the incoming angle is going to be the same as the outgoing angle. In other words, the angle of incidence.
Bros never fake.
Reflection.
Bro, did you see the
reflection.
shot he made on me in connector?
So if that angle was 25 degrees, then it comes out at 25 degrees.
He's freaking cheating, I know it.
Refraction,
Well,
however,
maybe they are
is a little bit more interesting, at least.
Bro, look at these hours on the game.
So if we look at refraction,
Hours is not everything, People buy accounts.
Into a material. So in this case, let's just say I'm going to draw normal. This time I'm going to draw it all the way through.
One down.
And let's say I have some angle. Yeah, it doesn't matter. But let's just say I have some big incoming angle like this right here, theta 1. And what it's going to do is it's going to pass from a material of one optical density to another one. So this could be, by the way, we define this as N1, and we say this is N2. I better define N right now, so just saying that this was for reflection. So N equals an index of refraction, and it has no units. Okay, for air, for example, we say the index of refraction is
Come
pretty
on, boys.
much
One more
1.
round.
So we say for
Can I
air,
get
n
knocked off,
equals
like?
1.
Yes,
So,
you can get.
In this
Thank
material, let's say this is air and this is maybe water down here. Okay, so this is sort of the surface here. This is where light goes from air to water. This actually happens where the light coming in at an incoming angle, I mean, sure, some of it may actually reflect, but we actually don't care about that part. We're going to look at what the angle of a light is that goes through. And it turns out that the light will actually slow down as it goes from, let's say, air to water, because it goes to something that's actually sort of thicker for it, in a sense, so optically thicker. So in that sense, because it slows down, it turns out that the angle, right here, this theta 2, is going to be smaller than theta 1 if it went from air to water. But keep in mind, it can go
Oh
from
my
water
God.
to air. In other words, it can speed up. And it doesn't have to be light. This could be anything. I mean, this could be a water wave that's entering a different type of density. That can happen. So we've got all sorts of situations. But theta 1 is not equal to theta 2. In fact, they're related by this. It's called Snell's law normally, but this is actually in your equation, or your data booklet, sorry. So it's n1 over n2 equals sine theta 2 over sine theta 1. And that's also equal to v2 over v1. So this is actually what's in your data booklet. This tells you how the index of refraction of one material is related to the next, and how the angles, so the incoming angle or the refracted angles, are related to each other. Notice this is a 1 over 2 for the ends, and yet the angles here, so theta, they're 2 over 1, 2 over 1. And that's actually because what's really going on is that we have n1 sine theta 1 equals n2 sine theta 2. That's actually what's happening. In other words, if you took this and put it up here and put this one, put it up here, you'd have n1 sine theta 1 equals n2 sine theta 2. And that's actually what's happening. For some reason in the data booklet they chose to write it like this. Fair enough. But I think another important thing to try to keep in mind is this. That's also equal to the wavelength of the second material over the first. So this is not in your data booklet. This is maybe worth keeping in mind, is this little piece right here. So that's not on your data booklet, but I think it's important. And I think the key thing here to remember, though, is this, that when light or a wave or something like that refracts, right, when it goes from one angle to another, the important thing that happens here is that although the angles will change, and the speeds will change, and the wavelengths will change, the frequency does not change. So the frequency of a light will be the same. You might wonder, well, how in the world can that be? Well, it turns out, remember that V equals F lambda. F actually stays the same, and the V's might change, the lambdas might change, but the frequency does not change when you have refraction. A neat example of refraction could be, let's say you're in the water, and you look, you have your hand sort of halfway in the water. You ever looked at your hand and it looks like your hand is broken, it's sort of bent? That's actually because the light is actually refracting, that the angle of a light is actually different in the water as it is out of the water, because light's actually going slower in the water than it is in the air. But remember now, it doesn't have to be that this is air and this is water and it always goes from big angle to small angle. It could actually be the opposite. Light could be going from water to air. I mean, that can happen. Or things can be going from one material to another. It could be, I don't know, going from air to jello to, I don't know, something else, maybe molasses, and then through some honey. I mean, who knows? Each of these things is going to have a different index of refraction. As long as you know that, you can actually work out what happens at that interface, right, between two different materials. An important property of waves is something called diffraction. Now, diffraction is all about the spreading out of waves when they go through some sort of hole or an aperture. So maybe we better define it that way. So diffraction is just the, so when waves go through an aperture. Now an aperture just means a hole of some kind. So when they go through an aperture, they spread out. And this spreading out, that is the diffraction. It's the spreading out of these waves. So what this means, this could be light waves because light diffracts. This could be a water wave because water also diffracts really well. And maybe I'll use water as an example. So let's say we have some sort of situation where we have some sort of opening where water waves can pass through. So maybe it's a really big opening here. Maybe that's a big wide opening here. Now this opening, what I'm going to do is draw the size of this opening will be D here. Okay, that'll be D. That'll be the size of the opening. Now this right here then, this will be the actual sort of wall here. This is some sort of wall. I don't know what this is. This could be anything. Could be solid wall here. And we're just measuring the distance. So let's say these are water waves coming in. So if we look at a top view of a water wave, maybe this is like the wave fronts coming in. So maybe they look like this. Something like this. So as the waves are coming in, maybe they have this direction right here. So this is the direction of the waves here. So as the waves come in, they're going to go through this hole. Now what's important then to look at is this distance right here. So this distance, that's the wavelength. So from one wave front to the next wave front, that's the wavelength. And if you look at this, the hole is much bigger than the wavelength. Okay, that's going to be the key thing here. So if D is much greater than a wavelength, we're going to see what happens here. So it turns out what happens is not much. In other words, these waves, they're still going to have the same wavelength, so maybe I'll just try to draw them again. So they're pretty close together like this, weren't they? Something like this. I'm just trying to draw them roughly the same as what they should be here. So something like this. So whatever they started out with, except here they're going to spread out just a little bit. So at the ends of here, they might spread out a little bit. So they'll go something like this. Okay, so they spread out only a little bit. In other words, these waves didn't really change much in shape. So this right here, we can say if D is greater than lambda, not much diffraction. They don't spread out much. Okay, so this could be sort of a key thing here. So if the distance, in other words, if the opening is much larger than the wavelength, there's not much diffraction. It doesn't spread out much. Not very exciting. But what happens then if our opening is quite small compared to the wavelength? So maybe I make the opening like this instead. So again, I'm going to draw it the same way. So here's my little wall somehow. And this is D here. This distance right here, that's D from here to here. So now the D is very small. And if I take a look at these waves again, maybe I make them like this. Let's say I had them coming in like this, these waves. Or again, this is the wavelength. Well, if the opening is smaller than the wavelength, then they'll actually diffract more. So now we're going to see things more like this. They're going to sort of spread out as they go along. And of course, this is the direction of travel of the wave, just to show you. So the wave is coming in like this. It's going to spread out more. So then the distinction we can make is that if D is less than lambda, we can say there's more diffraction. In other words, more spreading out. More diffraction. So this is the key thing happening here. So you see that that's the difference between, well, that's how we can get more or less diffraction. It's all about the aperture compared to the wavelength. So if the aperture is very small compared to the wavelength, there is more spreading out. And if the aperture is large compared to the wavelength, not much spreading out. And actually, my poor wife, I've been so excited about when we go, we have a little summer house. So it's like a little cottage that's near the water up north. Now I'm in Denmark is where I live. So north of Copenhagen, we're sort of near the sea. And so our little house, we walk about 10 minutes and then we get to the ocean and it's beautiful. But the place where people go swimming, this actually happens. This is the coolest thing is I see this diffraction effect every time we go swimming. So imagine then that this is us, this is like a top view, this is the coast here. And what they do is they have these little artificial beaches that are sort of made like this, and then they have these big sets of rocks here. And then another artificial beach and a big set of rocks. And this is a top view. So what you're doing then is the people, if you look at this then, as the waves come in from the ocean, the waves are coming in like this. These are like all rocks here. They're made to break the big waves coming in. Because if you're like a little kid swimming, you don't want giant waves crashing over you. So what they do then is in between these rocky places, and then here there's some, here it's all beaches, so people are all playing along this beach here. And if they want to go swimming, they swim in here. Well, what happens then is that these things, the openings here, are actually smaller than the length of the waves. So what happens is this, as these waves come in, they totally diffract like this. In other words, I see these waves coming in and they completely spread out. And I was so excited when I saw this. I was like to my wife, I said, oh my God, there's diffraction. She's like, what? Come on, can't we just go swimming? But I was just so excited because this exact effect was happening. If you're a water wave coming in from the ocean, and these are the rocks, these are a little place where they've put some rocks here, a little opening, what happens is then these waves totally spread. And this is where we'd be swimming. We'd be swimming along here, where in this example, it's just flipped upside down. My drawing is maybe not very clear. I think I'm just going to erase that. But I think you get the picture. So you can actually see diffraction in everyday situations. Sound waves can also diffract when they go through an opening. So in other words, the sound can actually spread. And light does the same thing. So these could be wavefronts of light. And this light can go through an aperture and they can spread. So diffraction happens in all sorts of situations. It's pretty
Guys,
not just
no
if you're
chance.
swimming
These
and
are my
your,
friends
poor wife
on the
who's
other
just trying to
team.
go swimming
No
with
chance.
you.
They
But,
won't
this works
let
for
us
any
take
situation.
around. They're gonna rage on us.
Is hacking or?
Yeah, there are 5 cheaters. They're all my friends.
Really? 5?
5, yeah. Yeah. I don't even mind reporting them. They're not gonna get banned.
Why not, man? Can you explain? It's just
Yes,
for
because they're my friends.
information.
I know. They never get banned. We play 2
Why
matches.
not? You know why?
They play 2 matches per account
Waves
every day.
Ah, yeah.
So you can't get
Now
enough reports to
interference is when
Overwatch.
two
You
waves
need
meet,
you need
they
like
might
11
actually
reports
interfere with each
Yeah.
other. It's a
or
bit
more.
circular to talk
Yeah,
about a definition within its
Too
own,
bad.
Okay, this is very good.
talk about
And
a term
maybe
within
you
its
can
own
tell your
definition.
friend don't
But let's
win,
just
okay?
state this.
Yeah,
Simply
no.
the definition
They're
of
gonna
it
rage
is
now.
a situation.
Believe me.
So when
If they're not,
two
if they weren't going to go
waves
obvious, now they're going full rage. Look at his
meet,
name tag, game
Yeah,
sense.
that's hacker, yeah.
interfere
yeah.
with each other. And I'm going to
Rest
explain
in
what I mean
peace.
by that.
My rank.
GG.
With each other. So,
Okay.
if I have two waves meeting, well, I'll show you the two extreme examples. Because by the way, when things are interfering, it can be completely constructive interference, we can have completely destructive interference, and we can have anything in the middle. So
They
I'm gonna
wrote
show you the
for
two
they wrote
extreme
to me. They're
examples.
gonna play on my
So if we
health.
have constructive interference.
Give me Deagle.
What
Give me
happens
Deagle.
then?
You are cheater too?
If we
No.
have fully constructive interference,
Give
well,
me
here's an
Deagle.
example. What if I have a little
I
wave
give
going
you
like
Deagle
this?
if you cheat, okay?
Whoa. Like maybe this is
I
in a
don't cheat,
string or
man. I'm
something like
streaming.
that. And then I also have another wave.
Rest in peace.
Maybe I'll draw it in blue. Whoa. And I
just
have
push
these
B.
two waves are on the same string. I'm just trying to show you two different colors here, but one's coming this way, and the blue one goes this way.
Won't that be?
Okay, so
One
like
headshot.
they're on a collision course. This could be on a jump rope. You know, if I
Nice.
take a long rope and I sort of,
Sit.
I make an oscillation this way, and I can make a wave travel.
Nice.
Keep in mind that would be a transverse wave because the oscillation goes up and down, and yet the wave would travel 90 degrees. To that. Now this you can do with a string or a rope, right? You just have one person at one end of a rope and the other person at the other, and you each at the same time, let's say, you make a little wave. So I make one going this way,
Why
my
not?
friend makes one going this way.
Oh
what
my
happens
god.
when they collide.
There's no way, guys.
But when
I
these two meet, if they're
suggest
exactly
you
the
stop
same size
trying.
and they're lined up really nice, we can have pure constructive interference, which means this one right here, what'll happen is this, that my white one wants to do this, and my blue one also wants to do this. Because you know when they're lined up, they're superimposed over each other. And the result is, at every point, all you have to do is add up the height of the wave. Each of the waves. So here I would add up this height plus this height. That means it would actually go twice as high. That means it would do something like this right as they meet.
Low
Then of
HPB.
course, after they meet, what would happen? Well, then we have the same
Are you sure,
situation
clear?
where afterwards we have this wave this way, and we have this wave this way. And this one still goes this way. This one
What
still
about the
goes
one in
that
car?
way. This is an
Yeah, that's
example of
not
sort
A.
of before,
Just go plant.
during, and after. But these
That
two waves will actually just
one
run
low HP.
right through each other. The interesting thing happens right in the middle. We call it
Nice,
constructive.
nice, nice, nice.
Because if you look,
Let's
it
do
sort
this
of
shit,
builds
boys.
upon
Come
itself.
on.
It makes the wave
I
bigger
swear to, I'm going
than
full try hard
it's
now.
been.
Let's do this
So
shit.
that's pure constructive.
We have like
We can also have
0.001%
destructive.
chance to win, but let's try.
No, but the opposite. So maybe I have a wave
Easy
like
win.
this. Maybe it goes like this. Whoa.
Not easy
And
win.
then over here, I
Look,
have
if
a
we
wave
win
that goes
enough
like
rounds,
this.
they're gonna rage. They're gonna spin both. I know.
So let's assume they're the same
But
height and everything.
let's-
They're moving
let's
in
just
opposite
try.
directions then. Except this one's opposite like this. Where do you two meet? Then I've got, my dotted line. This is what this white wave wants to
Side.
do. And this blue wave wants to do this.
Have that.
So what happens in reality? Well, at every point, I add up this value and
going
subtract
to
that
work
value.
once.
So in other words, it's going to be completely destructive. So right as they meet, the wave will actually go
Nice.
silent, so to speak. Or not silent, but it won't move.
Watch out, be toxic.
And then, of course, they'll
Come on,
pass
Max, watch
right
out, blue,
through
watch
each
out,
other.
blue, watch out, blue.
So that means in the end, what do we have? Well,
Go
and
ahead.
there goes my little blue chalk. It actually broke into a lot of pieces, but that's okay. So then afterwards, it goes like this, and my white one
Oh.
passes right through. My white one goes
Oh my
this
god,
way.
guys. If we do this, that's gonna make my week, not my day,
So that's
but
an
my
example
fucking week. I'm gonna
full
media them so
destructive
hard. I'm gonna
interference, and
clip
here
this
we
clip
had
and publish it
full-on
everywhere.
constructive interference.
That's good, bro.
I don't want you to think that these are the only two situations. You can have any combination of the two.
You see
Easy
this?
win.
You
Key
see
thing
this
here
first
is to just
dude?
think about,
Yes.
well, if they're
Yeah, he paid
nothing but
$500 for his
destruction,
cheat.
so to speak. But when you have interference, it just means
Yes.
add up
$500?
all the different
Yes.
points and see what you get.
Wow.
Now we can have something else too. We can have
1 half
interference
HP
in this
mid,
case.
blue
What if
mid.
we have light, let's say, or even a wave or something like that?
Okay.
But if we have light, let's say, and it's going through a little slit, so a little hole here.
It's getting harder.
The light's going through some sort of
Oh.
opening
Come
here.
on, team.
So the
Go
light
back.
goes
Let's
in
save.
through
Let's
this
save. Let's
opening.
save. Let's save. Let's save.
And what
Okay,
happens
good.
is, if we project it onto a screen,
Or shall we just give it a
the
shot?
light here can actually, well,
Lol.
it can actually diffract. The light
Easy
can
to
actually
kill.
spread out, like we just learned about. So let's say I'm looking at this point right here. That means the light that goes, from this top part may go, that distance, whereas the light
One is
from this
forward.
part, it goes that distance.
Flash out, wait.
And the key thing to keep in mind is this. The light from the top part didn't have to travel quite as far as the light from the bottom part. In fact, if these were parallel rays, because a lot
Top
of
to
times
the
they're
left,
drawn
top
as
to the left,
parallel,
top to
because
the
this thing
left.
we're gonna assume it's
Look, fuck
really,
it, I'm
really far
cheating. I'm
away.
gonna give you info.
So then
Top
we
to
would
the
actually
left.
assume that these two things are actually parallel. We would
You
actually
cheat too?
assume, they do something like this.
Very good.
Something like this. right
Let's
here.
do this shit.
We would say, well, then we have a, actually, you know what? I'll just keep it the way I had it. So let's say we have it like this and like this. Forget about the parallel part. It's actually not so important. If we look at this then, look at the distance that this one traveled compared to that one traveled. There's a difference in the
Rest in
path. In
peace.
fact, I can sort of draw it right here. So this,
Why you make them rage?
that
Yellow.
distance right there.
They're gonna rage. Don't
That's
say
how
the
much
word rage
further
one more
this
time. They're
lower
gonna.
one has to
Because
go
we would
than
lose
that
this
one in order to
anyway,
get
so
to that
yeah.
point. So we call
You
this
are
right
so
here, we call that the
pessimist, man.
path,
German
difference.
pessimist.
because it had to go
CG,
farther.
CG op. SSG.
And the key thing is this, and this is actually on your data book.
Wow.
So if the path difference,
Yeah, one man.
if it equals, so maybe I'll say if. So
If,
if
sorry.
path difference equals n lambda, Then we have
One vent. Yeah, he's
constructive
cheat.
interference.
Watch,
That's
I will one tap him. Watch.
Let's go.
We better define what this means. Okay, so this one right
Go,
here,
go,
this
go,
is
go,
really
defusing.
important here, is that if the path difference,
Oh, nice try.
in other words, if one of them had to go n times lambda more
What the fuck?
than the other one, then these two things are going to be in this kind of situation where they're going to interfere constructively and make things, well, if this was the light,
Oh,
this then
okay,
would be a
for
brightness
sure.
of the light. So this would be a point right here where
I
this would
don't
be
see.
really
Oh
bright
wait,
light.
he defused. I thought he
Now,
gonna leave us
lambda
around
is
just
the
like to piss
wavelength,
us off,
and
but
n
never mind.
is just some integer. It's just some number. So n is going to be, for example, 1 or 2 or 3 or 4 or 5 or whatever. So it's going to be a positive value, and it's going to be either like 1, 2, 3, whatever. In other words, as long as the path difference is a multiple of the wavelength, then you're going to have constructive interference. And we also have the
Yellow, I
opposite.
know
So
you're
if
cheating too. Please try hard.
path difference,
No, I don't cheat.
You
man.
are cheating. Shut the fuck up.
Fucking cheater.
You read
this
that.
time, what if we have it equal
Oh, wieso
to
cheatest du,
n
Mann?
plus 1 half times
Wo cheat ich
lambda?
denn rein?
So this is
Keine
another
Ahnung, der hat's
situation.
gesagt, der ist Cheater, der
The
ist ein
path
Cheater.
difference is basically,
Jawohl.
it's not just a multiple, it's actually a half multiple. So this would be,
Let's admit.
again, n would be 1, so this would be like 1.5 or 2.5
flash.
or 3.5. In other words, if it's a half multiple of this
Left side setback.
wavelength, then we have what's
Oh,
called
wow, he's
destructive
fucking us.
interference. So these are the two situations here that you might want to deal with. So on an exam question or something like that, these are the things to keep in mind. Oops, I'm writing really bad today. So this right here, this is what you keep in mind. You take a look at the path difference and see, is the
No
path
bullets.
difference a multiple of the wavelength? If so, constructive interference. You have this happening where it grows, it does more. Whereas if the path difference is, let's say, 1.5 lambda or 2.5 or 3.5 or 4.5 lambda, that's what adding the half does. Then you have destructive interference. That means at that point, let's say the path difference here was, let's say, 1.5 lambda. In other words, this little bit right here was 1.5, what the wavelength is. Then at this point, you'd have no light. You'd have a dark spot. So in other words, you could then scan along and then see what you get. You could actually get bright spots in the middle, and then darker spots, then
Oh
bright
wait,
spots,
I wasn't.
and darker spots.
I was
and
supposed to
bright
write
spots.
that in the journal.
So this is
That's
actually
not
what
here.
light does when you have what's called a single slit diffraction, right? So that's something that you can actually look at. Now we go into this in more detail, and one of the
Low HP.
not
Oh, blue is
advanced, one
hacking
of the
too.
additional
Very
high
good.
Every-
level
Very good
so
hack.
the one about
You
wave
have
function.
You have
fucking
hack.
aim
So
lock,
actually
bro. I
that's
saw this.
It's called sight and wave phenomenon.
You're funny, guys.
That's
You're
actually
very
option A.
funny.
So in that one, we go into this a little bit more detail. Basically, this is the underlying idea behind it, though, is as long as your path difference is either a multiple of the wavelength or a half multiple of the wavelength, you could say, then you either have constructive or destructive. You could have anything in the middle, and then you'll have, a combination of destructive and constructive and destructive. So remember, these are the two extremes here. But that's how interference works, and that's the end of what we need to look at for topic 4.
Guys, no chance. For real. I told you, no chance. Look, they would rage Swimbot and they would not let me win.
You have fucking noob friend.
Topic 5 from Physics SL as well as from HL is called electric current.
Say
And
your
it's mainly
friend,
about
suck my
circuits.
cock.
So that's the first thing I'm going to go over a little bit of basics about circuits. And I always find that students have an immense amount of trouble understanding what the relationship is between current and voltage and resistance. So I'm going to show you an analogy that's going to help you to understand it, hopefully. This is an analogy that you may not have seen before. A lot of teachers like to use water as an analogy. So, you'd say that, okay, well, the flow of water is like the current. And there's some good things about that analogy, but there's also some misconceptions that come up from that one. So what I'd like to do is actually show you a different analogy, and hopefully that will help to understand a little bit more about what's going on. Keep in mind though, I mean, this analogy is just to help understand what current, resistance, and voltage are, but it's not the same. I mean, obviously that's what an analogy does. It helps you to understand, but it is not equal to what you're doing. In other words, circuits are circuits. You know, electricity is electricity. This is just a way to help to visualize what's going on, because I find this especially is a bit abstract, and it's hard to, I mean, it's easy to understand, you know, something flies off a cliff, where does it land? That you can imagine that. But then when you're doing circuits, sometimes it's not so easy to imagine. And I think that's why circuits are sometimes more of a challenge. So first of all, before we can even start about that, we need to understand about charges. There's not much to write about them, because a charge is just, it's either positive or negative, and most particles will have either a positive or negative charge. So for example, electrons, they have a negative charge, and you know, protons have positive charge. Neutrons have no charge. Actually, that reminds me of a really bad joke about electricity, so I'll share it with you, so you don't have to laugh.
Huh?
But a neutron walks into a bar, he orders a drink, and then he asks how much it costs, and the bartender says, for you, no
Or
charge.
we will kick you, bro.
Oh, that's bad.
Kick me,
That's
but I'm
really
not
bad.
surrendering.
I've got an even worse one. Let's see, what is it? Oh, a hydrogen atom walks into a bar. It doesn't even have to be walks into a bar. Hydrogen atom says to his friend, hey, I think I've lost my electron. His friend says, really? Are you sure? And he says, yes, I'm positive. Okay, so let's go on to circuits here. So charge, first of all, charge is measured in coulombs. Actually, there, maybe I will say that. So charge, we use the letter Q for it, and it's measured in coulombs. Okay, a C like this. And in this analogy I'm going to show you, we're going to try to keep in mind that coulombs are, they're preserved. In other words, we have a conservation of charge. So the analogy I'm going to show you, well, first I'm going to show you a circuit diagram, and then I'm going to try to explain a bit of what's going on. So first of all, here is a circuit.
You can kick me, I'm not
This right here is going to be
surrendering.
the world's most boring circuit, because it's just, oh, I made that a big battery here. So this right here is a battery. This is the symbol we use for a battery or a terminal. And this just represents a wire going around. So I could just have any old battery. I can